nucleophile carbonyls 1, 2, 3, 4, 5 being the carbonyl of the nitrile. We now have carbon 1, 2, new bond between 2 and 3. 3 is still bound to 4, which is bound to, I'll just keep all the atoms in the same place, 5. And 5 is the carbon that's triply bound to the nitrile. Okay? You can write it like this. You can also simplify it. CF3, 1, 2, 3, 4, 5. And have that just be a nitrile there. Okay? Good. So there's multiple ways that you can draw this. I'm going to go back to the structure right here, and I want to just show you resonance through the nitrile, okay? So if we resonate, or if we draw the arrows for resonance, the lone pair will form a pi bond between carbons 4 and 5, breaks the pi bond between 5 and the nitrogen and pushes the electrons onto the nitrogen. So we generate a resonance form where we can stabilize that minus charge on the electronegative nitrogen. Just like we would on an oxygen of a carbonyl. Okay, I'm just not sure if you've been shown this before, so I just wanted to show you that resonance structure. Okay, good. All right, so one of the take-homes from this example is really the fact that if you have a nitrile, it's going to be similar to having like an ester group there. Good? Yeah? All right. Okay. So what we're going to do now is we're going to start to transition into more of the amines section, okay? We're going to just do a little bit within the amines section, but these next examples are going to tie together the amines with the carbonyls. And what we're going to talk about are reactions of enamines. Okay. So enamines are what we call enolate equivalents, okay? And that is because there's a resonance form where the nitrogen lone pair can come down to form, let me zoom in, come down to form a pi bond, breaks the adjacent pi bond, and can generate a nucleophile at the alpha position. So the lone pair minus charge at the alpha position. And we have the nitrogen now with 4 bonds. Okay? This is the same type of arrow pushing we do for the resonance form of the enolate, where we have lone pair from oxygen comes down to generate the pi bond, and the electrons will localize at the alpha carbon. Okay? Do you see the similarity between the two? Okay? This is how your body makes enolates. Okay? Your body has a lot of amine-containing compounds, including side chains from your amino acids, and they will condense with ketones and esters, well, ketones and aldehydes, to form enamines that will allow it to undergo enolate chemistry. Okay, so when you see an enamine, I want you to think about the fact that this is going to be an equivalent to an enolate, meaning it's going to be nucleophilic at the alpha carbon. So this is nucleophilic at the alpha carbon. Okay, so the same things we did with enolates, we will do for the most part most of what we did, we can do with these enamines. So the first reaction that we looked at with enolates was where we just added an R group to the alpha position. We call that an alkylation. Same thing is going to happen here. So you can think about the resonance form, or you can draw all the R's at the same time. I'm going to draw the resonance form first of this enamine so that I can see the reactivity at the alpha carbon. So I'm just going to draw everything as it was. Now I have a double bond between the nitrogen and the carbon. Lone pair, minus charge at the alpha position. Okay. Here's my nucleophile. I'm going to do the same thing now that we did with the enolates. Lone pair will attack at the carbon where my leaving group is located. Okay, so this is our alkyl halide, or maybe there's a tosylate group on here. But we have nucleophile, attack the electrophile, kicks off the leaving group. And what that's going to do is it's going to generate a new bond between the alpha carbon and that carbon with the leaving group. All right, so I'm going to redraw my nucleophile exactly as it was before. Ooh, stop erasing on me. Does anybody know how to turn that off so it stops erasing? Does anybody have an Apple Pencil that like...
Oh yeah, you have to go, you mean like when you press?
Is that what I'm doing?
Yeah, you're pressing too hard. If you go to your settings,
Uh-huh.
and you can like turn it off where like I used to have that problem, so if you don't click the sides anymore, then it will stop changing.
Perfect. In general settings then?
Yeah.
Thank you.
Click your Apple Pencil.
Thank you, thank you, thank you. All right, so here's my structure as it was before. We have removed, we have pushed the electrons to the alpha carbon. It made a new bond. That new bond is between the alpha carbon and the carbon that had the leaving group, which I'm going to put a little green dot on. So here's that carbon, and that carbon had whatever R double prime is attached to it. Okay. All right, but now we have this positively charged nitrogen. And the way that alkylations with enamines work, and in your body or in nature as well as in the laboratory, is that we want to usually get this to come off and give us back our carbonyl. Because the whole thing is to be able to make an enolate equivalent and have it react without needing a strong base around or a base at all, okay? So if you can form an enamine, which we'll talk about that again in just a minute, you can have this chemistry happen without any base around, okay? But we want to get back a carbonyl, and so to do that, we're going to react water. So what water will do with an acid catalyst is take the double bond to nitrogen and replace it with a double bond to carbon. Oh, sorry, to oxygen. Okay? It does what's called a hydrolysis. And you probably did this in the aldehydes and ketone chapter, but it's probably worth reviewing again if that's okay. All right. So we're adding acid and water, so that means that we have H plus and H2O floating around. That's what that means. So the lone pair on oxygen is going to attack the carbonyl carbon or the iminium carbon and push the electrons up to the nitrogen. Everybody okay with that? Yes, no? Okay. If you don't see why it's attacking there, think about the fact this has a resonance form where the pi bond is broken, the electrons are localized back up at the nitrogen, and you have a plus charge at what I'm going to call the carbonyl carbon. Okay, those are resonance forms of each other, where we've taken the pair of electrons and localized them up to the nitrogen. That's why oxygen attacks there. Okay? After it does so, we now have something that's going to look like a hemiacetal, but it's called a hemiaminal. Never going to ask you that. Where we have an amine and an oxygen attached to the same carbon. Okay? So when we run this reaction, we swamp it with tons of water. So we're going to use Le Chatelier to push us to form this product by just swamping it with water. So what will happen now is that we will have a proton transfer happen, or if you prefer, we're going to remove a hydrogen from the oxygen and have a hydrogen added to the nitrogen. Do you guys prefer if I show that or just write H plus transfer? H plus transfer is fine? Okay. H plus exfer. So I'm redrawing this backbone. We have an equilibrium where we now have the nitrogen protonated. Good? So far, so good? All right. Now, we're going to have the lone pair on oxygen come down to form the carbonyl, and that kicks off the nitrogen. And look where we are. I keep dropping off the prime there. R prime, R double prime. Double bond to oxygen with a proton. And we've generated the amine as well. And now the amine or water, something will come along and pull off that extra proton so that we can neutralize the product. And that gets us our final products. Okay? Good? Questions, comments, concerns? Okay. So if we put together our two parts of this reaction, where first we make the enamine, and then we react the enamine, and then hydrolyze the enamine, we can get an aldol product under non-basic conditions. So I'm going to do that in this example below. So I'm going to label a lot of what I just said as well. Let me just make this a little bit smaller. Okay, so now we're going to combine three things. So we are going to combine, one, we're going to make an enamine. Second, we're going to use that enamine as an enolate equivalent. So we're going to use as enolate equivalent. And three, we're going to hydrolyze. How do I spell hydrolyze? I know I just read that. Hydrolyze. Is it Z-E-D or S-E-D? Z? I think unless we're in Europe, they would probably write S-E-D. Okay. This is going to allow us to do an aldol type reaction or a use of an enolate under non-basic conditions. So this is avoiding it avoids basic conditions. Avoids basic conditions. Okay. Awesome. All right, so you can imagine in your body, you don't have like LDA floating around, right? That would be a really bad thing. So in your body, this part right here is going to come from either an amino acid as part of a protein in the active site, or another biological molecule is going to be your nitrogen. What it does is it's going to add to a carbonyl, makes an enamine, reacts like an enolate, and then gets hydrolyzed back off. Okay? So if you've taken a biology class and you've learned about like enzyme complexes, okay? I always learn them as E plus S makes ES. Do you guys remember this? So enzyme plus substrate makes enzyme substrate. That becomes enzyme product, and then we release the product. Can you kind of visualize that if you've had biology? Okay, this is exactly what's happening in this reaction. Step 1 is E and S coming together to make ES. Okay, step 2, we're making EP. And in step 3, we're releasing the product and regenerating the enzyme. That's what happens, okay? So what we're gonna do in step 1, and I'm not gonna do all the arrow pushing for this, so this is a great place to practice arrow pushing. We're gonna do a little bit more arrow pushing later. So in the first step, we're going to do a condensation reaction where we are taking the carbon oxygen bond, and we're going to convert it to the carbon nitrogen bond. Okay? So after step 1, so this is step 1, we have a nitrogen that is, oh, let me actually draw it differently here. We have a nitrogen that brought with it 2 methyl groups attached to a carbon, which was the carbonyl, and we have the double bond. So I'm going to number carbon 1, carbon 2. Carbon 1, carbon 2. So you may be saying, Nolan, you said we're going to make a carbon-nitrogen double bond, okay? We are, in a way, it is the resonance form, where the lone pair on that nitrogen comes down and generates the enolate equivalent. When that nitrogen shares its pair of electrons to form the pi bond, it becomes positively charged, and we generate our enolate equivalent, okay? Because nitrogen is bringing in 2 R groups of its own, the 2 methyl groups, there's no way to have it have a double bond and neutral, okay? Everybody with me? I know we're all tired. I should have brought sugar or something today. I'm sorry. I'll bring it to the final. Okay, so here we go. We made our enzyme substrate complex. Now we're going to react it. So now in step 2, what we're going to do is introduce the electrophile. This is my electrophile. Oh, I can spell. No, I can't. That's my electrophile. I have an acid chloride. Okay. This looks weird, I know. But let me go off to the side here and ask you, if I had this acid chloride and the nucleophile I added to it was hydroxide, what would you do? What would you make? You'd do a substitution, right? Addition, elimination, and you'd end up with the nucleophile in place of the leaving group, right? We're doing the exact same thing. Exact same thing. So after step 2, what we're going to do, it's like a little poem. Step 2 is going to substitute the nucleophile, which is this whole thing, that's my nucleophile, in place of the leaving group. So we have the nucleophile, and we have the leaving group. Okay, so, oh, I'm writing this so big I can't even draw it there. Come on. There we go. Okay, so I'm gonna draw my electrophile. In place of the leaving group, I have a new bond to the nucleophile. That nucleophile's new bond is attached to carbon 1, which is still attached to carbon 2, which still has a double bond to the nitrogen, which has its 2 methyl groups, and the plus charge. So I have added on what I'm going to call carbons 3 and carbon 4. Carbon 3 and carbon 4. Okay? It looks different than what you did before, but it's really not. Okay? So if we're using our enzyme analogy, we just went from ES to EP. Now we need to release the enzyme and give off the product, which means we need to release the nitrogen compound. Okay? So we're going to undergo hydrolysis. Okay? The mechanism is what we did above, right up here. Okay? And what that's going to do is it's going to take the carbon-nitrogen double bond, release the nitrogen, and get us back to carbon-oxygen double bond. Okay? So that is going to give us carbon 3 still attached to carbon 4. The new bond that was formed over the course of the reaction, which was to carbon 1 from carbon 3. That is still bound to carbon 2, which now has a double bond to oxygen. And that was carbon 2. Okay? So this is putting together old stuff with making enamines with new stuff, which is enamines acting as the nucleophile. Okay? Everybody's just so tired. Okay, can you see how those go together? All right. So let's just do the same nucleophile, and let's now have it do a Michael addition, aka the addition to the beta carbon, just like we did before. Okay? So now we're just changing up what the electrophile is. We've done two different ones now. The first one was just an alkyl halide. We did an SN2 reaction. Here we used a acid chloride, which is going to do the addition elimination. And now we're just going to switch it up and use the alpha beta unsaturated carbonyl so that we can add to the beta position. Same thing. We're going to have our nucleophile attack. So I'm going to draw, once again, I'm going to draw this out as the enolate equivalent just to help with as much clarity as we can give. Oop, that's a pH minus charge, lone pair. So what we did was we brought the lone pair for the nitrogen down to form the pi bond, which breaks the adjacent one, and those electrons localize at the alpha carbon. Okay, these are just resonance forms of each other. Okay. Now we can have that nucleophile that we just made add to the beta position, pushes the electrons to the alpha carbon, just like all the Michael additions we did before. Okay. I'm going to number starting here 1, 2, 3, 4, and 5, and 6. Okay. So what we've done now is we've made a new bond between 2 and 3 and broke the bond between 3 and 4. So here's my nucleophile. Double bond to the nitrogen with the 2 methyl groups, plus charge on the nitrogen. So that is carbon, or those are carbons 1 and 2. New bond to between 2 and carbon 3. 3 is still bound to carbon 4, which is bound to 5 and 6. Putting in my 4, 5, and 6. And we have now a lone pair minus charge on 4. So one thing that's really handy and really useful as you go through this in all reactions actually is to remind yourself that charges have to stay the same, okay, overall. Meaning I started with overall neutral, which means that at every stage I have to have overall neutral unless I add a charge of some sort. So here I'm still at overall neutral, okay? So after we do this, this is the conjugate addition. We add in step 2, H3O plus, which is gonna have 2 roles, okay? Any idea what the first role is? What is it gonna be? H plus, good. It's going to be an H plus donor. So it's gonna act as an acid. I like to write it out like this so I can show the bonds breaking and forming. So carbon 4 is going to grab the proton and release water. That's going to first to give us the neutral product. Sorry, not the neutral product, the cationic product. So new bond, 3, 4, 5, and 6. Okay. I brought in a plus charge in that step, so I do have a plus charge overall. Then it's going to do the hydrolysis because this double bonded nitrogen with the 2 R groups is not stable. Okay. You introduce water in an acidic environment. We're going to do the hydrolysis. Once again, the mechanism for that is above. But hydrolysis is going to take the double bond to the nitrogen back to the double bond to the oxygen. And we get our Michael addition product, which is, as always, a 1,5 dicarbonyl. So if I put in my numbers, 1, 2, 3, 4, 5, back to 6, the 1,5 dicarbonyl. Whew. Good? Yeah? All right. So what I have down here at the end, oh, is everybody done writing? Yeah? Okay. What I have down here at the end are the patterns that we make of the reactions, okay? So the reaction names are off to the side here. Here are the reaction names. All right. And the way that they are, oh, they were not consistently colored. Sugar booger, I'm sorry. We have nucleophiles that I will highlight in yellow. So these are the enolates. Oh, no, they are colored. They're all in red. So the red is equal to the enolate, the nucleophile. Red equals enolate. which is our nucleophile. And the product part that's in blue is what came from the electrophile. So the blue is from the electrophile. And the green, thank goodness, is kind of showing up, is the new bond. And let me highlight that. I don't know if it'll give me green. No, it won't give me green. That just looks like yellow. Yeah. Okay. So I tried to use the words a lot as we did them, so you kind of got used to hearing them. But these are the patterns that you should be getting. So for example, if on the final you're gonna do a Michael addition, it's helpful to know that the product should always be this 1,5-diketone or dicarbonyl. 1,5-dicarbonyl. Okay, because it may be an aldehyde. Okay, so it's a good way to like double check yourself. Whew, how are we feeling? Good? Bursting with fruit flavor? You guys don't know that, do you? It's a commercial for Fruit Loops. Do they still have Fruit Loops, the cereal? Yeah, it used to be like bursting with fruit flavor. Okay, all right. Just a little bit more to go. And we're gonna talk about enamines. I'm sorry, we're gonna talk about amines. Woo, which is the last section. All right, so we've seen amines do a lot of things over 2 semesters of orgo. And this is gonna be 90% a review with some different words. Also, I hope included in that 90% is talking about basicity of amines in aromatic rings. I'm getting from the look in your eyes, this is not going to be a review portion. Okay, this is really important, so we'll get to that. All right, so let's just start by saying, what is an amine? A little philosophical conversation here. Well, unlike ethers and alcohols, amines have varying patterns of substitution. We have everything from NH3, which is, what's NH3? Ammonia. Okay. To a nitrogen that has one R group, and we call these the primary amines. Okay, just like we would call a carbon a primary carbon if it has one carbon attached. An amine with one R group attached is going to be a primary. And we have our nitrogens that have 2 R groups attached. They're going to be secondary amines. I bet you can guess what they're called if they have 3 R groups attached. Tertiary amines. These are tertiary amines. And nitrogen will readily add a 4th R group, more readily than oxygen will make a third or make a bond to a 3rd R group. And these are called ammoniums. Sugar booger. Ammonium salts. So you often will see this ammonium with something like chloride. Okay, you probably in Gen Chem saw NH4Cl a lot. Ammonium chloride. Does that sound kind of familiar? Like I probably saw it sometime. Okay. So these are kind of the gambit of nitrogens with varying amounts of single bonds to hydrogens and R groups. So nitrogen is going to act as both a nucleophile as well as a base. So we have seen, probably you saw last semester in 205, where a nitrogen nucleophile, so here I have a plus charge on the sodium, which means my nitrogen has 2 lone pairs and a minus charge. Okay, this is going to be a strong nucleophile, so it can do an SN2 reaction pretty readily. So the lone pair on the nitrogen will come and make a bond to carbon, kick off my leaving group. So what that does is it's going to add an R group onto the amine. So we're adding 1, 2, 3 carbons, new bond to the nitrogen, which brought with it 2 hydrogens. Okay, so the other thing we make is sodium bromide, but here we made a primary amine just by doing an alkylation reaction, adding an alkyl group on. Okay. In the carboxylic acid chapter, you learned that nitrogen can act as a nucleophile and displace a leaving group on an acid chloride derivative. So now it can act as a nucleophile. Electrons go up to the oxygen. We make a tetrahedral intermediate, Me2HO minus. We have a good leaving group so that when the oxygen reforms the carbonyl, it's going to kick off chlorine. And oops, I forgot a plus charge on my nitrogen there. Sorry about that. Okay, so now what we've done is we've replaced the nucleophile for the leaving group. So I have a double bond to oxygen, phenyl, new bond to nitrogen. That nitrogen has 2 methyl groups and a hydrogen on there. And what do you think happens after that? Oh, yeah.
I just had a question for the deprotonation.
Yes.
Does it matter if we do it before or after kicking out the leaving group? Like, I thought there would be a proton transfer.
Yeah, so the question is when do we pull off this proton, right? So there's a chance it could transfer off before we collapse back down. I don't know that we know necessarily when that happens. So if you transfer it off before, that's fine. Yep. Good? Yes.
If we drew it kind of in one step without the intermediate, with pushing the electrons up to the O and then like having them come down the other side and kicking off the leaving group, do you want us to draw the intermediate?
Yes. Yeah. Draw the tetrahedral intermediate, yeah. So are you saying to basically have this arrow go all the way around and kick this off? Or are you saying add the arrow and then kick that off?
Like keep the arrow going up to the oxygen and then like have another one coming down the other side.
Yeah, just break those up into 2. Yeah. And that's really useful to really be able to see the difference between the carboxylic acid derivatives and the aldehydes and ketones, and that aldehydes and ketones don't have this leaving group and get stuck there. Yeah, good question. So we'll remove this proton. You could either do it right beforehand, you could have a proton transfer, or afterwards, have another amine come along, pull off the proton, electrons to the nitrogen, so that we end up with our acyl substitution product, aka the amide or the amide. Okay. Good? All right. So first one is kind of 205 chemistry. Second one is definitely 206 chemistry. And so is the third one. if we react an amine in the presence of an acid catalyst, we really need that acid catalyst, with an aldehyde or a ketone, we will lose water and replace that carbon-oxygen double bond with a carbon-nitrogen double bond. Okay? And you probably have heard me use this word before. This is a condensation reaction. Okay? So we're losing water, and so this is a condensation reaction. And you saw that in the aldehydes and ketones chapter. Okay? So this is 205 chemistry. This is carboxylic acid chapters. And this is the aldehyde ketone chapters. Cool? All right. Do you feel comfortable with those three reactions? Yeah? Okay. So let's talk about where my notes just went. Amines. Here we go. All right. So some new things and old things, it's going to come up when we talk about amines being bases. All right. So I'm going to start with just kind of the overview of amines as bases, and then we're going to get specifically into amines in aromatic rings, okay? Which is what you guys are saying you did not see before. Okay. So amines as bases. Amines can be bases when they're neutral as well as when they're negatively charged, okay? If a neutral amine acts as a base, its lone pair will grab a proton from an acid, kick off the conjugate base of that acid, and we make an ammonium salt. So here is the ammonium part plus A minus, okay, where the conjugate acid of the basic ammonia, so I'm going to label the amine as a base, reacting with the acid. It forms the ammonium as a conjugate acid, and then we also made the conjugate base. Okay? Not too bad, right? Okay, this is a moderate base. The negatively charged nitrogen is a very strong base, okay? So when we have a negatively charged nitrogen acting as a base, grabs the proton, we make an amine, a neutral amine, as the conjugate acid. Okay? So negatively charged amine is a good strong base, strong. The pK of his conjugate acid is up around, pKa is up around 38. Okay? Why do I mention the pK of the conjugate acid? Because if this is a strong acid, it's going to push in this direction. Is 38 a strong acid? No. So there's a really good driving force this way. Okay? I like to talk about it that way as opposed to saying it is the conjugate base of a weak acid, so therefore it's a strong base. That to me sounds like. So by thinking about the fact that this acid has a pK of 38, which means it's really weak, which means it's not going to push the reaction very easily backwards. It's going to stay here. So we have a really good driving force to go forward. The ammonium has a pKa around 10. Okay, much stronger acid, much more likely to be forming an equilibrium depending on what the acid is. A reversible deprotonation. Does that make sense? Okay. So as we start talking about the basicity of amines that are in aromatic rings, we need to have a little refresher about aromaticity, okay? So first we're going to talk about what does a nitrogen have to have if it's going to act as a base? What does it have to have? Like down, a negative charge or a pair of electrons, okay? In order for either of these nitrogens to act as a base, they have to have a pair of electrons they can use to make a bond to the hydrogen. All right, so in order to act as a base, an atom must have a lone pair available to act as, actually, let me change that to form a bond to hydrogen, to form a bond to H plus, okay? If there's no lone pair available is going to be the key word here, available, then it's not going to act as a base. All right. So let's take a look at these two molecules here. So I know I wrote this down someplace. Where is it? Ah, sugar booger. Okay, hold on. Dun, 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 dun. I have to look up. Mm-hmm. Mm-hmm. What is the name of it? One moment, please. PK just like went out of my head. Pearl. There we go. Okay. All right. So here are two amines. And those two amines happen to be cyclic and part of an aromatic ring. Okay, so let's start with first things first. Do you feel like you could recognize both of these as aromatic rings? So what do we have to have for aromatic rings? Let's just write these over here. Oh, sugar booger. Aromatic. Okay. You have to have a continuous cyclic ring system, right? So it has to be a continuous pi system. Okay? So there's a long way that we say that. A continuous cyclic arrangement of parallel p orbitals is a long way to say it. Continuous pi system, it has to be cyclic. And how many electrons are there in an aromatic ring? There's multiples. Something n plus something. 4n plus 2. 4n plus 2. So that means if I have a continuous pi system that's cyclic and I have 2 electrons in it, 6 electrons in it, 10 electrons in it, and so on and so forth, that means that it will be aromatic. Any questions about that? Because we have not talked about this at all. Yes?
How many, what's the rule, I forget, what's the rule of lone electrons on it, like added to the ring? Like, if there's more than 2 lone pairs?
We're going to do that right now.
Okay.
Yeah. Okay. So let's talk about these two examples and we'll hit that. Make sure I answer that question. So here are two nitrogens that are in a ring with a continuous pi system. All right. So in the first one, it may be a little bit more kind of in your face to see that we're alternating double, single, double, single, double, single, right? Okay. In the next one, you may say, well, I don't see that pattern because I have a nitrogen. The nitrogen's lone pair is going to be in a p orbital, and that p orbital will be part of the pi system. Okay? Have you looked at this before? Okay. Let me show you what that means. So each of these nitrogens is sp hybridized. This nitrogen and this nitrogen. Okay? The one on the top, we can actually see the double bond to it. Okay, so there are 3 things attached to this nitrogen, a lone pair and 2 carbons, so it's sp2. You may look at the nitrogen that's in this ring in the parole at the bottom here and say, well, there's 4 things. There's a lone pair, there are 2 carbons and a hydrogen, so it should be sp3. And my answer to you would be, it would be if the double bonds were not there. So the nitrogen, and you don't have to draw this if you don't want to. I'm going to kind of draw this from the side, kind of looking this way. That's an eyeball, by the way. Here's the like lashes. That nitrogen puts the lone pair in a p orbital and has everything else attached to it through sp2. Okay, that is a small space to put a pair of electrons. It normally wants to be in a hybridized orbital. It does so that that orbital with those electrons is parallel to the 2 pi bonds that are there. What that does is that puts the electrons into position to resonate with the rest of the electrons in that ring. So now we're able to have the lone pair as part of the pi system. Okay, we can draw that resonance by showing the lone pair coming down to make a pi bond, which breaks an adjacent pi bond. I could put the lone pair on a carbon. Okay, so we have that resonance form, and we can draw another resonance form. But maybe by looking at this resonance form, you can see where that nitrogen really is sp2 hybridized. Okay? So that's going to make the lone pair on this nitrogen in parole that I'm highlighting here in yellow be very different in how it will react with an acid than the lone pair that is on the pyridine, which is up top. Okay? So one of them is going to be a very strong base relative to the other one. So the pKa for pyridine's conjugate acid, pKa, you do not need to know these numbers, is 5.2. Okay, that's a moderate acid, right? Moderate. It's not strong acid, it's moderate, which means it will pretty readily go back and forth in this equilibrium, depending on the pH of the solution, but relatively speaking. Would it surprise you that the pKa for the conjugate acid of my other amine down here in parole is 0.5? You're like, nope, I have no idea what that means. Brain hurts, brain tired, ouch, stop. Right? Is that kind of what your brain's saying about now? Okay. What this is telling me is that this acid is 5 to the 4.7 times more acidic. okay? So if we round that up, 10 to the fifth is what? 100,000 times more acidic? Wow. That's a huge difference when you start to think of it that way, right? If you start to think about 5 versus 0.5, you may not see it, but when you start to say this one up top here is 100,000 times more stable than this one, that's a big difference. So let's figure out why, okay? So the one on the bottom here is getting into that strong acid territory. It really, really, really wants to go back in this direction. So this is a strong acid. Oh, more acidic, okay? And the reason is, actually, can anybody think about why that is? Part of it has to do with the question you asked. Part of it has to do with what I just drew right here. Yeah.
I mean, I don't know for sure, but it's just,
Yeah.
so when it's in the strong acid, it's not a continuous pi system.
Yes.
So because of that, it's really like just out of whack, basically. So
Yeah,
it has to go
it is
back
very much out of whack.
so that it can
Absolutely.
recreate the.
That's a great answer. Nice job. So, try not to throw things as well. When we go from the structure on the left, pyrrole, to its conjugate acid, we break that conjugation, okay? This is now an sp3 hybridized nitrogen. It has 0 lone pairs on it. It has 4 sigma bonds attached to it, okay? We broke resonance. We broke conjugation, which is bad, costs energy. Not only that, but before we had a continuous cyclic arrangement of parallel p orbitals, continuous continuous cyclic pi system that had how many electrons in it? 2 from this pi bond, 2 from this pi bond, and if we're resonating the lone pair, there are 6. So this is an aromatic ring with the lone pair resonating as part of that aromatic ring. So for that to act as a base, it has to break aromaticity, which costs a lot of energy, and form the bond. So once it does that and forms this acid, it's like, dude, no, like I don't want this proton, take it away so that I can take the lone pair and become aromatic again, okay? So why is it more acidic? Nitrogen must, or I should say ring, sorry, let's say the ring must break aromaticity, ring must break aromaticity for the nitrogen to be basic. Okay? The one on the top, it does not have that problem. Okay? That nitrogen has a pi bond to it already. So it cannot have a pi bond and have a lone pair resonating at the same time. So this nitrogen, in this case here, has, I'm going to draw it from the side, has a pi bond already drawn to it, or already, that it's already participating in bonding with. Okay, so we have this side-on view here where we have the pi bonds going all the way around. I should have used different colors for that. I apologize. Let me clean that up a little bit. Let me just redraw it. I'm just going to use different colors, but I'm going to redraw it the same way. Nitrogen, carbon, 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 back. We have one pi bond here between nitrogen and the carbon next door. Then we have another pi bond here. Okay, so this is the blue one. This is the green one. And we have one more pi bond here. Okay? How many electrons are in those 3 pi bonds? 6. So this is an aromatic ring. So this is aromatic without the lone pair resonating. Okay, that lone pair is actually sticking straight out from the nitrogen. Lone pair, and it's in an sp2 hybridized lobe. Okay, so pyridine literally has like a lone pair on the end, like, let me find a proton, let me find a proton, let me find a proton. And there's nothing that it has zero communication with the pi system. Okay, so if the nitrogen in the ring has a pi bond drawn to it, okay, and a lone pair, only the pi bond can be part of the aromatic ring. All right? If the nitrogen has a lone pair but no pi bond, then that lone pair can resonate with it. Okay? Let me write that down. Okay. So, if we have nitrogen, lone pair, and a double bond, lone pair cannot resonate in the ring. I'm going to draw the rest of the ring in black here. Okay. If we have the nitrogen with a lone pair and no double bond attached to the nitrogen, that lone pair can resonate. No pi bond on the nitrogen, then the lone pair can resonate. Was that the rule that you were asking about?
Yeah.
So you can kind of only contribute for each atom one pi system?
Exactly.
Okay.
Yep, because those p orbitals that are overlapping are in one plane, and as soon as you try to do another one, they're in a different plane. Yep. Good? All right, so let's take a look at this molecule. Does it look vaguely familiar to you, like you've seen it before? Does anybody know what this is?
Is it a hormone?
It's a what?
A hormone?
It's not a hormone, but it is that what you said, a hormone?
Yeah.
It's actually part of your DNA. Okay, so what is which one?
Well, it's not purity, it's purity.
Is it adenosine?
Adenosine.
I should write this down. DNA base structures. No, it's actually that's guanine. Oh no, it was that one, adenosine. Actually, it's the same. They're the same. So depending on what else is attached to it, it could be here. It would either be your adenosine or your guanine. So your A and G bases. But it's the foundation of the DNA. Okay? So it'd be good to know if the nitrogens are basic or not, wouldn't it? It's kind of something important. All right, so let's try to figure out which of these is basic and which of these is not basic. And when we say not basic, what we're saying is that the lone pair is tied up in resonance. Lone pair tied up in resonance. Okay? That's what we're going to mean by lone pair, by non-basic. All right. So first I'm going to go through and make sure everything has a lone pair. So that nitrogen, I see 3 bonds, so it does. 3 bonds, it does. 3 bonds, it does. And 3 bonds, it does. Okay, so all of these have a lone pair. All right, so let's just start up here. And so what we want to know is the lone pair tied up in the resonance of the ring? If it's resonating, then it's not basic. If it's not resonating, it is basic. Okay? Is the lone pair on this nitrogen resonating? No, because that nitrogen already has a double bond. So is it basic or not basic? Basic, good. So this one's basic. How about, I'm just going to go like clockwise. How about this one?
Basic.
That one is basic. Lone pair is not resonating in the ring. Okay. How about this one? Basic.
Really fast.
Yes.
Double checking.
Yes.
We count the double bonds as 1, 2, like for SP.
Yes, absolutely. So the way that I describe it is how many things are attached. The thing can either be an atom or a lone pair. So this nitrogen here has 2 atoms and 1 lone pair, so it's sp2. Okay? All right. And then how about this one? It is not basic. Why? Because this lone pair can resonate with the rest of the electrons in the ring and be part of an aromatic ring. So this is not basic. Okay? So your DNA bases, at least A and G, are going to have 3 basic positions on them and 1 that's not basic. Okay? Questions on that one? All right. Let's rank these, and then we're going to stop, I think, at that one. We won't do reductive amination. But let's talk about these 3, and let's rank them as far as most basic to least basic. Okay? They each have a lone pair on them. Okay? Anybody have an instinct? Yeah?
The middle one's gonna be the least basic,
Least basic. Why is that?
because it's doing the most resonance in the ring.
Yeah. So this is going to be resonating not only just within the ring, but within an aromatic ring. So resonating within aromatic ring. Okay. What about the next 2? Do you want to make a statement about either the first one or the last one? Yeah.
I mean, yeah, the one on the left is
Uh-huh.
gonna be the most basic,
Most basic. Why is that?
because it's not doing resonance at all.
It's not doing any resonance. No resonance. Okay. The one all the way on the right, it's resonating, right? We have a lone pair next to a pi bond. It's not part of an aromatic ring, so it's not as tied up, but it's kind of tied up. So there is some resonance. Okay. I wanted to get to reductive amination, but I think you will survive without learning about reductive amination. But at least we got this, which I think is going to be really important if you're getting into biochemistry. And if you're not, then you learned something about your DNA bases, that this is what the foundation of A and G looks like. Okay, couple things as you're wrapping up your stuff. I am going